morning, welcome to new lecture. Today I will talk about new topic, moment distribution method, or they call it Hardy-Cross method. Let's see, what is this method? Moment distribution method. Or they call it Hardy-Cross method. It is an iterative method in order to solve indeterminate structure. One method which is very well known, we already talked about that, it was slope deflection method. If we have a structure with higher degree of indeterminacy or higher degree of freedom. For example, let's look at this frame. This frame, it is 1 degree freedom, only rotation, for example, A, B, C. So in slope deflection method, it is good method in order to solve this frame. But if we have frame something like this, as an example, multi-story building. For example, here, how many degrees is indeterminate? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 3, 27 degrees. This system is indeterminate, or if we look at the degree of freedom, so degree of freedom 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12, the 12 rotational degree of freedom. Translation, if you convert all these to the hinge, you need add one member here, another member here, another member here in order to have this frame in equilibrium and make it stable. So 1, 2, 3 plus 3. The degree of freedom is 15. So if you solve this frame using the slope deflection method, you will need 15 equation, 15 unknowns you will have. So in order to find 15 unknowns, you will need 15 slope deflection equation, and that is difficult to solve. So here, moment distribution method or Hardy-Cross, it is much easier and faster. Let's see how we can solve indeterminate structure using moment distribution method. I will explain the procedure, then I will solve the several examples, then I will explain the concept. So first I will explain the procedure, then I will write step by step how you will solve different examples using moment distribution method. I will solve example. After that, I will explain the concept. This method is invented by Hardy-Cross. Hardy-Cross was from our area. He born in 1885 in Suffolk, Virginia. I know I have students this semester, they are from Suffolk, Virginia. He passed away at 1959 in Virginia Beach. Virginia Beach City, Virginia. And for a short, for a short term, he was faculty in our university, Old Dominion University. He used to teach in our school. Of course, in that time, our school name was not Old Dominion University, but he used to teach in Old Dominion University for a short term. And he is from our region, and if you are interested, you can go and visit his graveyard or cemetery. Last year I went and I visited and it is interesting place. If you want, if you like it, go visit. His mother, father, wife and himself, all they are neighbor, and it is cemetery in Smithfield, Virginia, 20 miles from here, and the cemetery name, it is Ivy Hill Cemetery. So this is about Hardy Cross. It is good we learn this method very well because he is from our school and our region. Let's see, he published paper in 1932 and he came up with this method in his paper. In order to solve indeterminate structure using Hardy-Cross method, first you should be able to calculate memory stiffness and carryover factors. I prove this, and then we will use only the result. So, what is the memory stiffness? How we can find it? And carry memory stiffness and carry over factor. For example, if we have this beam, one end is fixed, another it is roller support, I apply moment M here. I will have, if this is MA at point A, this is B. This, if I apply moment M, let's say I apply in this direction, positive direction. So the form shape will be something like this, and I can calculate theta A. So here I apply moment MA. Here, because we have fixed support, the theta is equal to 0, but I can find this theta A using, for example, slope deflection method. How I can find that? MAB is equal to M fixed AB plus 2EI over L 2 theta A plus theta B minus 3 psi. We know this slope deflection formula. I proved it before. So here, let's see, because we don't have external load, this term is equal to 0. Because it is fixed support, this term is equal to 0. And we don't have any lateral deflection or settlement, this term again is equal to 0. From here, MAB will be equal to 4EI over L theta A. So if I find MAB over theta A, it will be equal to 4EI over L. Moment divided by the rotation or slope created by that moment in this system is equal to 4EI over L. It means the rotational stiffness for this system, KAB, it is 4EI over L. So the rotational stiffness for one beam, if we don't allow point A moves in vertical direction and we have another end fixed or continuous, the rotational stiffness, it is 4EI over L. So we should memorize this. Let's look at to the rotational stiffness. Before the rotational stiffness, let's see if I apply M here, what will be the reaction here? How much will be MBA? If I apply here, moment is equal to the M here, what is the reaction at the B side? I can calculate again using slope deflection method. MBI is equal to M fixed BI plus 2EI over L 2 times theta B plus theta A minus 3 psi. Again, because there is no external load, this term is 0. Because there is no settlement or lateral deformation, the support A and B, both of them in the same level, so the psi is equal to 0, and because the B end is fixed, this term is 0 too. From here, you will find 2 EI theta A over L. So I can write MBA is equal to 2 EI over L times theta A. What was the theta A? Theta A was equal to M AB over 4 EI over L. I found that. If I apply at point A moment M, so MAB will be equal to the M, theta A will be M divided by 4 EI over L. I can plug this here. If I plug that, MBA will be equal to M over 2. It means if I apply moment M here, the reaction in this side will be M over 2. So the carryover factor for this system is equal to 1 over 2. You apply M here, half will transfer this side. So the carryover factor will be equal to the 1 over 2. That is one thing we should know. Let's look at to see if instead of this beam we have simply supported beam, what will happen? Instead of this beam, if we have simply supported beam, and I apply moment MAB here, this beam will deform like this, a little bit, if I show more precisely, it will be something like this. Okay, I apply MAB here. Let's see what is the theta A. If I write the slope deflection formula, MAB is equal to M fixed AB plus 2EI over L 2 theta A plus theta B minus 3 psi. That will be equal to, this term is 0, this term is 0, will be equal to 2EI over L 2 theta A plus theta B. MBA moment in another side will be M fixed BA plus 2EI over L 2 theta B plus theta A minus 3 psi. That will be equal to, again because there is no external load, this term is 0. There is no settlement, this term is 0, will be 2EI over L 2 theta B plus theta A. If I apply moment MAB equals M here, the moment here it is 0. MBA will be equal to the 0 because this is hinge. If I plug this equal to the 0, I will end up with theta A is equal negative 2 theta B. So the rotational slope here is 2 times of rotation here at point B, and it will be in inverse direction. You see this rotation is counterclockwise, this is clockwise, so one of them is positive, another negative. If I plug that here, instead of theta A, I can put, for example, in terms of theta B, what I will get. If I plug that here, I will get, instead of MAB, you can put M is equal to 2EI over L times 2 theta B, that will be negative 4 times theta B plus theta B. That will be this will be 3, let's see, that will be 3 years. If I plug that, that will be 3 over theta B. Okay, let's see. If I apply moment M here, now I can find the relationship between M and theta B. That will be equal to, let's say remove this part, that will be equal to M is equal to 2EI over L negative 3 theta B. That is equal to negative 6 EI theta B over L. Because theta A was equal negative 2 times of theta B. If I want to represent in terms of theta A, I should plug, instead of theta B, theta A divided by negative 2. If I plug this here, this will be positive, negative times negative will be positive 3 EI over L theta A. So from here I can write MAB over theta A is equal to I can write MAB over theta A is equal to 3 EI over L. This means if I apply moment M here, if I apply moment M here, magnitude of the moment M, and the slope here is equal to the theta, that moment divided by theta will be equal to 3 EI over L. This is rotational stiffness if this end is hinged. So let's now compare these two rotational stiffness. If I compare these two rotational stiffness in this system, if far end is fixed and I apply moment M, the deflection will be something like this. This is theta, and M over theta, which is rotational stiffness, will be equal to 4 EI over L. If far end is hinged, I apply moment M here. This will be theta. Here M over theta is equal to rotational stiffness. It will be equal to 3 EI over L. So Now we know what is the rotational stiffness if the far end if it is fixed, and what is the rotational stiffness if the far end it is hinged. And the carryover factor here, it was 1/2. It means if I apply M here, the half will transfer to the fixed support. That carryover factor here is equal to 0. Because if I apply M here, the moment in far side here, it will be 0. It is hinged, there is no internal moment. So, in order to solve indeterminate structure using moment distribution method or Hardy-Cross method, first step, you should look at the rotational stiffness for each member. If the far end, if it is fixed or continuous, the rotational stiffness, it is 4EI/L, and the carryover factor, it is 1/2. If the far end, it is hinged, the rotational stiffness, it is 3EI/L, and the carryover factor, it is equal to the 0. We should know that. Then we should calculate the distribution factors. Let's look at to see how we can find distribution factors. Distribution factors we will show with DF. For example, if we have frame like this, and this is point A, point B, point C. The stiffness for this member will be KAB. The stiffness for this member means rotational stiffness, KAC. The distribution factor for AB will be equal to KAB divided by summation of stiffness. That means KAB divided by KAB plus KAC. Distribution factor for member AC will be equal to KAC divided by KAB plus KAC. So distribution factor for each member will be equal to rotational stiffness for that member divided by summation of stiffness of all members reached to that joint. Let's look at the next example. For example, if our frame is like this. A, B, C, D, KAC, KAB, KAD. Okay, here distribution factor for member AB will be KAB divided by KAB plus KAC plus KAD. Distribution factor for other member, again you can calculate in similar way. Let's look at one joint with 4 members. For example, you have frame like this. Joint A, KAB, KAC, and KAE and KAD. So point A, B, C, D, E. Here, for example, distribution factor for member AB will be equal to KAB divided by summation of stiffness. K, A, E. So this is the way we will calculate the distribution factor for each member. Distribution factor will be equal to the stiffness of that member divided by summation of stiffness of all members reached to that joint. Okay. Of course, this joint should be rigid joint like this. You see, if one of them is hinged, it will not be summation of all. If all of them, it is rigid joint, something like that. Let's see what we will do then next. So after distribution factor, we should know something important. What is that? The summation of all distribution factor, I am writing here, all of the distribution factors for the members at a single joint must add up to 1. So if you have one joint and you have different members, for example A, B, C, D, E, and so on, the summation of distribution factor for member AB plus distribution factor for member AC plus distribution factor for member distribution factor for member AD plus distribution factor for member AE should be equal to 1. This is the way you can double check to see you calculate these distribution factor right or wrong. So the summation of all distribution factor should be equal to the 1. Okay. Let's see another important point you should know. So first of all of the distribution factors for the member at a single joint must add up to 1. This is one important thing you should double check. Another one, the distribution factor for a fixed end the distribution factor for a fixed end support will be 0 and the distribution factor for a pin with only one member connected will be 1. Why the distribution factor for a fixed end support, for example, will be 0? Because if, for example, this is member AB and we have, of course, other members. Look at here. The distribution factor for member AB will be stiffness of member AB divided by summation of stiffness of those members comes to the joint A. One side you have member AB, so the summation of stiffness of member AB plus summation of stiffness of the ground. The summation of stiffness for ground, it means the stiffness of earth. So here the stiffness goes to infinity. If you add infinity here, number divided by infinity will be 0. For that reason, that distribution factor will be equal to the 0. Let's look at today the moment distribution method steps for beams. I will summarize the steps and then I will solve one example. If we have enough time today, I will solve example today. Otherwise, next session. Let's see. Here, moment distribution method for beams. Step by step. First step. What are the steps? The moment distribution method for beams. Let's say add here the moment distribution method for beams may be summarized as follows. Step 1. Determine the stiffness means rotational stiffness for each member. We know the formula we will use. If far end it is continuous or fixed, it is 4EI over L. If far end it is hinge or pin, that will be 3EI over L. This is the first step. Second step, determine the distribution factors for each member at each node based on relative stiffness of the members. And it means distribution factor For one member like AB, it will be KAB divided by summation of members reached to node A. After that, step number 3. Step number 3, I should remove these. Step number 3, determine the fixed and moments for all members. Exactly, you had this step in slope deflection method. You will use the same tables, and our contract is the same. Counterclockwise is positive, clockwise is negative, rotation counterclockwise is positive, rotation clockwise is negative. So we will use the same contract. Of course, different book, they have different convention, and maybe they assume the clockwise is positive, no problem. But here we will follow the same direction we follow in slope deflection. So step number 4. Step number 4. For each node, we will do 2 things. A, determine the unbalanced moment on the node. B, distribute the unbalanced moment to each member connected to the node in proportion to the distribution distribute the unbalanced moment to each member connected to the node in proportion to the distribution factors in the reverse direction of the unbalanced moment. Pay attention. In the reverse direction, this is important. If the resultant unbalanced moment, it is clockwise, you will distribute counterclockwise. If the resultant unbalanced moment, it is counterclockwise, you will distribute in clockwise direction. Should be in reverse direction of unbalanced moment. Later on I will explain the concept, you will see why. So part A, part B for step 4 and part C. let's say write part C here. C, step 4, section C or part C, for each member that the moment has been distributed for each member that the moment has been distributed to carry over some of the moment to the opposite end of the member according to carryover factor. If it is fixed side, it is 1/2. If it is hinge carryover factor, it is 0. And last step, step number 5. Step number 5, repeat the previous step for each node. So the last step, repeat the previous step for each node multiple times as necessary until the carryover moments are a small fraction of the total moments. Then sum all of the moment in each member n. Okay, let's apply this to one very simple example, step by step, to see how we can apply and how we can solve indeterminate beam using moment distribution or Hardy-Cross method. We have very simple example. This beam, it is indeterminate, and the degree of indeterminacy, it is 2 degrees, we know. Here we have A, B, C. This span, it is 5 meters. This span, it is 4 meters, 2 meters, 2 meters, entire span is 4 meters, but we have one concentrated load 50 kilonewton here. We want to find reactions here. It is indeterminate structure and the degree of indeterminacy it is 2 degrees. We will use moment distribution method, and EI for entire beam it is the same and it is constant. Let's see how we can solve it. First we will calculate the stiffness for each member. KAB will be for EI over L. That will be for EI divided by 5. That will be 0.8 EI. KBC will be equal to 3 EI over L. That will be, because you see here KAB, the far end it is fixed, KBC, the far end it is hinged, so 3 EI over L. That will be 3 EI divided by 4, that will be 0.75 EI. So first step we will calculate the stiffness for each member, and we have 2 members, so we will calculate 2 stiffness. Next we will calculate the distribution factor. Distribution factor for member AB will be equal to KAB, which is 0.8 EI, divided by KAB 0.8 EI plus infinity, because it is fixed support. The other side it is the ground or earth, so that will be equal to 0. Distribution factor for member BA will be equal to KAB again, 0.8 EI, divided by summation of stiffness for all members reached to the node B. That will be equal to stiffness of member BA, 0.8 EI, plus stiffness for member BC, that is 0.75 EI. Answer for this will be 0.484. 0.484 distribution factor for, let's see, distribution factor for member BA will be the stiffness of member BA, 0.8 EI, divided by KAB, 0.8 EI, plus 0.75 EI. The answer will be equal to 0.516. The answer will be 0.516. Distribution factor for member BC will be equal to stiffness of member BC, 0.75 EI, divided by KAB plus KBC, that will be 0.8 EI plus 0.75 EI. This will be equal to 0.484. So up to now we find the distribution factor for AB, BA, BC. And now look at to here, these 2 members reach to the joint B, so the summation of this distribution factor BA plus distribution factor BC should be equal to 1. If you add these numbers, you will get 1, so that is right. The distribution factor for member CB will be equal to K BC, stiffness for member BC, divided by, again, summation of stiffness of members reached to the C. This member reached to the member C, other side it is ground. Because it is hinged, it is discontinuous. So we have only one member BC. The distribution factor for this will be equal to the 1. Because again this is hinge, this member stiffness divided by summation of stiffness. Summation of stiffness, it is 1 here, BC, another it is ground or earth, but it is not continuous. Hint, make it discontinuous, so only we have one effective stiffness. Divided together it will be equal to 1. Then after that we will calculate the fixed end moment. Fixed end moment for the AB part it is equal to 0 because there is no external load at the AB span. So M fixed AB is 0, M fixed BA is 0. But we can find M fixed BC, that will be counterclockwise, so positive PL over 8. PL over 8 will be 25 kilonewton meter. M fixed CB will be clockwise, negative PL over 8, that will be equal to negative 25 kilonewton meter. Now we will create one table. Using this table, always I recommend use some sort of table because it will make your calculation much easier and you will not make mistake. So, the table, in order to create the table, let's see, I have enough space here, hopefully I will have enough space. Joint, I have joint A, I have joint B, I have joint C. Joint A it is fixed joint, we know that. Joint B it is continuous part, joint C it is pin. Then after joint we will write the members. Member AB, member BA, member BC, member CD. So from joint A we have member AB, from joint B we have two members BA and BC, and from member C we have only member CD. Next, we will list the distribution factors for each member. Distribution factor for member AB it is 0, for member BA it is 0.516, BC 0.484, CD it is 1. Then we will write fixed end moment for members. It is for member AB it is 0, for member BA it is 0, for member BC it is 25 positive, for pin this side because it is clockwise negative 25, it will be fixed end moment. So for member AB it is 0, AB is 0, BA is 0, BC it is counterclockwise positive 25, CD it is clockwise negative 25. Then we will balance joint B, this joint. So we will write balance B. In order to balance B, let's see what we will do. We have this moment. It is positive. In reverse direction, we will make it negative. So instead of 25, we will have negative 25. That will be balance disjoint B. So it is positive 25, we will make it negative 25. Then negative 25 times this distribution factor will be negative 12.9. Negative 25, because it is in reverse direction, negative times this distribution factor will be negative 12.1. From this, we will have here another row carry over. From here, because the A side it is fixed, carryover factor it is half. This multiply half will be equal to negative 3.23. Sorry, this times half will be negative 6.45. This times carryover factor, because far end it is hinged, it will be 0. So carryover factor from this moment, if goes to the fixed support, it is 1 over 2. If goes to the pin support, it is 0. So let's see, this is carryover factor, this multiply 1 over 2, it is negative 6.45. This moment multiply 0, it will be 0. Then we will balance joint C. If we balance joint C, again, what is the fixed end moment here? Negative 25. We will make it reverse direction, so it will be positive 25. So positive 25 times the distribution factor, which is 1, will be 25. So balance C here, we will write it 25. So at joint C we have 25. Why 25? Because the fixed end moment it is negative. We will make it reverse direction, magnitude the same, the direction reverse. So negative 25 will be positive 25. Positive 25 times distribution factor, we will write here, it is 25. So carryover factor, it goes to joint B. Joint B is continuous, so carryover factor, it will be half. So carryover factor, it is half, 1 over 2. So here, carry over will be 12.5. After that, we will balance again joint B, balance B. Now, 12.5, we will make reverse, it will be negative 12.5. We will multiply to distribution factor. So here we will have negative 6.45, here negative 6.05. Again, carryover factor. Half will transfer here, will be negative 3.23. Carryover factor to this side, it is multiplied to the 0, it will get 0. Now we will add all these moments. You see what is the moment here. We have 0, we have negative 6.45, negative 3.23. So if we add sum of those sum for joint A, we will have fixed 0, one moment, another moment 0 plus negative 6.45 plus negative 3.23 will be negative 9.68. For joint B in the left side, BA side, so if I call this MAB, this will be MBA, BA. We should add these together, so we will add negative 12.9 plus negative 6.45. It will be negative 19.35. M, B, C, we will add 12.1 plus negative 12.5 plus negative 6.05. That will be again, let's see. Here I made mistake. Okay, for BC, we will add all moments together. 25 minus 12.1 minus 6.05. All moments. For AB and BA, fixed part was 0, so you add negative 6.45 to negative 3.23. Here negative 12.9, negative 6.45, but here we have fixed then. So 25 minus 12.1, let's see. We will have negative 25 minus 12.1 plus 12.5 minus 6.05. So all moments you will add together. If you add these moments together, let's see, you will get this, they cancel, 0.4, 0.4 positive, that will be, okay, that will be 19.35. So 25 minus 12.1 plus 12.5 minus 6.05. If you add together, you will get 19.35. MBA and MBC should be equal in inverse direction because summation of moment at joint should be equal to 0 in order to have that joint in equilibrium. So it is right. Here at joint C, let's see what we have. Negative 25 plus 25, this is 0. So negative 25 plus 0 plus 25 plus 0, they will cancel, address is 0. So MCB will be equal to 0, and it is right because this is hinge should be 0. So MAB negative 9.68, BA negative 9.35, BC 19.35, CB is 0. Now negative moment means clockwise, positive here means counterclockwise. We can cut these members and find reactions. So member A, B, positive, negative 9.68 means clockwise, 9.68, negative 19.35 clockwise, 19.35. So you can find this reaction. You can take moment respect to A. Find this will be 5.8. Summation of force in vertical direction equal to 0. 5.8. Member BC, free body diagram, 50. This will be 0. This will be positive, counterclockwise, 9.35. So if we take moment respect to here, we will find this 20.2. If we write summation of force in vertical direction equal to 0, we will find this 29.8. So for AB, we find moment and shear in both ends. For BC, we find moment and shear at both ends. Now we can draw moment diagram and shear diagram. So shear diagram, as much as reaction we will move at point A, it is 5.8 downward. There is no force, continue. B reaction at the left side 5.8, B reaction at right side 29.8. There is no force, continue, 50 down. If you come 50 down, then continue 20.2, move up, close the diagram. This will be shear diagram. Bending moment diagram. Moment here, clockwise. If you apply moment clockwise here, create tension underneath. So positive 9.68. Moment in this side, counterclockwise. Moment at BA, it is again clockwise. Clockwise moment here, if you rotate point A in the left side clockwise, create compression underneath of the beam, it is negative moment. So it comes from positive to the negative 19.35. Positive, negative. BC part, the moment it is BC part, let's see. At the BC part, moment was counterclockwise. Counterclockwise, if you rotate here, you will have compression, so again negative. At point C here, it is 0. This reaction here, it is 20.2. If I move from here to this side, what is the moment here? 20.2 times 2 will be 40.4. How it rotates? It rotates in this direction. If you take with rand and bend like this underneath, it is tension, so positive moment. Positive 40.4, and that goes to the negative. Okay, thank you so much for watching this lecture. See you next session. Next session I will solve more examples and then I will explain the concept in depth. For now, focus on the example, learn the procedure, then I will explain the concept. This is better way I think you will understand the concept. If I first explain the concept without seeing the procedure, it will be hard to digest and understand. Thank you so much. Have a nice day. Bye bye.